Hi, and thanks, and thank you all for attending. And today we're going to be talking about schema design for MongoDB and sort of more in general how to think about modeling data for non-relational data stores like Mongo. Before we begin, I'd like to push a poll to the audience to get an idea of everybody's experience level with MongoDB. So I am going to push the poll. And please feel free to check off the box that indicates, how much experience you have with Mongo. This hopefully will help me skip over introductory material if you guys are all really advanced, or focus on more of the basics if most of you are not super familiar with Mongo. So thanks for joining. Again, my name is Jared, and I work at TenGen. TenGen is the initiator of the MongoDB project, and I spend most of my time working with the developer community and some of our customers and partners in helping them adopt Mongo and use it to the best of its ability and to have successful deployments. So we find that when we're modeling data in Mongo, things work pretty differently than a relational data store. And so it's important to really understand the core data model of Mongo and in general to look at how you can really take best advantage of NoSQL data stores. So once again, if you want to follow me on Twitter, I am @Jared. I have lots of entertaining tweets to send to you, so please follow me. So what are we going to cover today? We're going to cover basically a bit of introduction of looking at how we use documents in the database and how this differs from using a relational database. And we're going to talk about how you evolve your schema in a MongoDB data store. Obviously, MongoDB has a completely dynamic schema, which means that you don't need to define what columns exist on your database before you start coding. You can just add them on demand as your application calls for it. We're going to go through queries and indexes and talk about some of the more advanced features of how you can combine multiple nested attributes inside of documents and some of the cool capabilities that come from that. Towards the end of the presentation, we're also going to go through some common patterns. So we find that common object-oriented design patterns and data modeling problems tend to have slightly different solutions in MongoDB. So we'll go through some of those solutions and look at how people are using Mongo to do this in their applications. So let's look at ways to model data. Right? Data comes in all kinds of different forms, and typically when we think about modeling data, we're coming from one of several different backgrounds. We're either coming from a relational background where we think about data as rows and columns and relationships and key constraints, although a lot of us also come from more of an object-oriented background where we think about classes and attributes and aggregations and associations. And historically, if you talk to a data architect, typically the first thing we're going to talk about is normalization, right? In a database, everything's very flat. You tend in a relational database to model things sort of like you would lay them out in a spreadsheet. And so in order to get the most mileage out of a relational database, we want to normalize our data to separate all of the different attributes into different tables, and that enables us to query effectively on these different things. However, what we found over the past few years is that as sites like Twitter and Facebook go to actually scale their data model, people tend to denormalize their models. The reason for this is that it makes it very difficult to scale your application when you need to use lots of joins and transactions in your database. Anybody who's had to try to scale a database beyond hundreds of millions or billions of rows probably has some experience with the complexity of managing joins and transactions at this scale. So when we denormalize our data model, what happens? Basically, instead of thinking about all the different rows and columns, we tend to think more on an entity level. So for something like modeling a blog engine, rather than separating out all the different things into different tables, we can aggregate like information together into documents. And we call this a denormalized data model. And this is basically how we think about modeling data in MongoDB. You tend to think about the high-level entities, the first-class citizens in your application, and how they're going to be represented and stored in the database. So first of all, if you're coming from a relational background, there's some terminology to get straight. So in an RDBMS, you have a notion of a table. MongoDB has a notion of collections, which is very similar to a table. In an RDBMS, a table is a set of rows. Well, in MongoDB, a collection is a set of JSON documents. Now, just like a relational database, MongoDB supports indexes, so we have the same idea of indexes in Mongo as you do in your RDBMS. And in an RDBMS, where you might use a join to collect information from multiple tables, in MongoDB, we tend to address this by using embedding and linking of information. So rather than joining data together across multiple tables, we can actually stick that data right inside the parent object that it belongs to. And that's going to be a lot of the focus of the rest of this talk of how that actually works and what some of the limitations and some of the optimizations you can make to make your application highly scalable. So when we think about modeling data in MongoDB, we tend to want to think about a few things. We want to think about how we're going to manipulate the data. So what kind of queries are we going to be running over it? What kind of indexes do we need on the data? What kind of updates do we need to be able to perform to objects? And Mongo also includes capabilities for doing things like MapReduce, which you might be familiar with if you've ever played around with Hadoop. MongoDB makes it really easy to use MapReduce because you can send JavaScript MapReduce functions right to the database. You don't need to maintain a separate Hadoop cluster in order to do that. In addition to the way we're going to manipulate the data, we want to think about the access patterns of our data. Right? So for example, for a given object, what's the read-write ratio? Is this an object that we're going to be updating a lot of the time, or is it something that's sort of written once and mostly read after that? And we want to think about the life cycle of our objects and how they want to live. Obviously, this is not terribly different than RDBMS, but some of the things that tend to be a little different in MongoDB is that MongoDB does not support joins. Now, the reason we don't do joins is joins are one of the biggest things that makes it difficult to scale a database horizontally. We find in a relational database, if we want to make our database work on multiple computers, rather than buying a bigger computer, joins tend to slow things down. The reason for this is that in a horizontally scaled database, when I perform a join, I typically need to talk to an arbitrary set of database nodes rather than being able to process a query on a single node. So by eliminating joins, MongoDB makes it way easier to scale horizontally. Now, we sort of make up for the lack of joins with a richer data model, and that's, again, a lot of what we're going to be talking about today. So let's take the example of modeling, say, a bookstore. Right? So I've got a bunch of books, and I want to store these inside my MongoDB. Well, so first off, before I go into this, let me point out that MongoDB as a JSON database essentially uses JavaScript as its sort of native language. So when you log into the database shell, analogous to, say, the SQL shell you might drop into in MySQL, everything is in JavaScript. So all the examples on these slides are actually JavaScript code. You can cut and paste these examples into your MongoDB shell, and they should work just as you see them here. So here what we've got, I'm creating a book object that has a bunch of attribute value pairs. So we have an author, a date, text, and tags. Now, comparing this to a relational database, most of this looks pretty similar. The attributes here are similar to a column in a relational data store. The only difference is that instead of declaring the columns on the table, I'm just embedding these directly inside of the document. Now, I can say db.books.save and this book object that I've just created. Now, what's notable here is what I didn't do. I did not tell the database that I have a table called books. Simply mentioning it from my application causes the database to actually create a new collection called books and save this new object inside of it. I also, like I said, did not tell the database what fields are going to exist in this collection. Instead, every book can have its own set of fields. The other thing you'll notice that's pretty different here from what you can do in a relational database is I have this tags field, which is an array of strings. Here I see it's a comic and it's adventure. So once I've inserted that document into the data store, now I can actually do queries on it. So I can say db.books.find and get my book back. Now this is a lot like saying select star from books in a relational database. Now you'll see that the object looks a little bit different than it was when I inserted it. First of all, we have the underscore ID field. This is essentially the primary key of the document in the database. You can specify a value for underscore ID, whatever kind of value you want. It might be the title of the book or its ISBN number, for example. But typically what people do is you just leave this attribute out and let the database allocate one for you. We have a thing called an object ID, which is a globally unique hash key identifier, and it's designed to work really well inside the database. You'll also see that the date field is expanded. In the previous slide, I just said new date, and here we see it's actually expanded to the actual date. That is actually a little bit of a misnomer. MongoDB internally actually stores dates as integer fields, and so they're much more compact than it looks right here. But in the shell, when I go look at a date, it's going to expand that date and make it more human readable for me. Now, once I've inserted some documents into the collection, MongoDB supports indexes, just like a relational database. So for example, if I want to create an index on the author field, I can say db.books.ensureIndex author:1. This creates a B-tree index on the author attribute of the documents in my books collection. Now, again, this is a lot like a relational database where, if you don't have any indexes and you perform a query, you're going to do a table scan where the database goes and looks through every object and compares it with your query. But if I do have an index that supports the query, it's going to perform much, much more quickly, especially in large data sets. So here I say db.books.find author:hergé. Forgive my poor French pronunciation, and now I find my book back. So this is a lot, the parameters of the find clause are a lot like the where clause in a SQL query. I can specify attributes in my documents that I want to match against, and the database is going to go find the documents that match that query. Now, MongoDB has internally a query planner and a query optimizer that figures out the best way to plan and execute a query. So I can access this from the shell using the explain command. Again, this is very similar to an RDBMS where I might explain a SQL query to find out how the database is processing it. And so here from the shell, if I say db.books.find author:hergé .explain, I see the explain plan for this query. This is going to tell me what kind of cursor it's using. Here I can see it's a B-tree cursor, which means it's using an index. I can see n-scans. This is telling me how many comparisons the database needed to do in order to find a match for my query. I can see the number of milliseconds that it took to run the query, and some other more advanced stuff like index bounds, which we'd get into in the detailed indexing talk if you guys wanted to attend that webinar whenever that happens next. Now, up until now, the indexes perform pretty much like you'd expect from a relational database. But now we're going to do a neat trick, right? If you remember earlier, our books object had a tags value, which was an array, right? And now I'm defining an index on that tags array. So I'm saying db.books.ensureIndex tags:1. Now, what's interesting here is in a relational database, if I wanted to store a set of tags on an object, typically what I would do is I would set up a second table, say a tags table, and I would have a foreign key that refers to an element in my books collection, and if I had 5 tags, I might have 5 rows in that table that refer back to the book. But in MongoDB, I can store arrays natively inside of the parent book document. There's no need to create a second collection. And indexes are smart, and they work with these data types. So when I define what we call a multi-key index, this is an index on an array field, it actually takes all of the individual values inside the array and puts them inside the index. So this means I can now do queries where I say, db.books.find tags:comic. And this is going to now go and find all of the books in my book collection that have a comic tag inside that tags array. Now you'll note I'm not matching the entire value of the array, I'm just matching an individual element inside of it. And so this is really neat. You're doing things like tags or keyword searches, I can do natively inside the document. I didn't need to do any joins. I didn't need to set up a second table. I can store all that information right inside the document. Now, MongoDB's query language, up till now we just are doing simple queries where we're matching on a single attribute, but we actually have a full query language, and you can combine together multiple fields. So I can match, for example, on author and publication date. I can do range comparisons, so find me all the books published between this date and that date. I can do logical queries like in and not in to do set comparisons. I can check the type of things, so find me all the books where the title is a string. That might be a useful query for you. We also have a set of update operations that allow you to perform atomic updates to a document. We're going to go into an example of exactly how you do this in a moment. So now we have our book inside the books collection, but we want to add comments, right? So you notice that there was no comments field inside the original book document. But what I'm doing here is a snippet of JavaScript where I create a new comment. So it's a comment from Kyle. It's got a date of when the comment was written, and he says it's a great book, and he's got 5 votes for this comment. And so now I can use the update command to actually push this comment onto a book. So I say db.books.update, and now update command has 2 clauses inside of it. The first is a query clause. So I'm saying text : destination moon. So this acts like the where clause of your query. So this tells us which book it is we want to update. The second part of the update clause is the actual update command, and I'm using 2 updates inside this single transaction here. So I'm saying a push command. What this does is this pushes a value onto an array. So when I say push : comments : new comment, what this is telling the database to do is on this document with the title destination moon, I want there to be a comments attribute that is an array, and I want you to push this new comment onto that array. Now, if the array doesn't exist, MongoDB is pretty smart. It'll add the array. I didn't need to tell the database that there was a new field. It simply adds it into the document. I'm also using the inc command. So inc is increment, and we're saying I want to increment the comments count field by 1. So once again, the comments count did not exist in the original document, so this command is actually going to create that attribute, initialize it to 0, and then increment it by 1. So now, when I go back and look at my document, I'll see that I've extended it. So we have the original document modeling my book at the top with the author, date, text, and tags. But now you'll see we actually have a comments field, which is an array, and it has my comment as a nested document stored inside of it. And I have my comments count field, which counts the number of comments that I have inside my document. Now, what's really interesting here is when you think about it from a data modeling perspective, in a relational database, I would have a number of tables at this point, right? I would have a table modeling my books. I would have a separate table for tags. I would have a separate table for comments. I probably would have another table for authors. And if I wanted to do any operations on this data, I really need to do joins and multi-statement transactions in order to play with this model. But in MongoDB, I can store all of this inside of a single document because, after all, most of the time in my application, I'm probably dealing with all of this data at the same time. And so by doing that, I get a lot of heavy optimization out of the performance of the database. Because since all this data is stored together, it's very fast to retrieve. I don't need to join data together that's stored at different locations on disk. And it's very easy to deal with because this is sort of the unit of information that my application is typically dealing with. Now, once you start adding things like nested documents and arrays, the syntax starts to get a little interesting. So we have this thing we call the dot operator, and this allows me to reach into documents and address fields that are stored internally inside of documents. So earlier we were doing a query where we say, find me all the books by this author. But what if I want to find all of the books that Kyle has commented on? Well, here I'm going to create an index on comments.author. And so what this does is the dot notation allows me to reach into objects. So comments, remember, was an array field that stored objects internally. And each of those objects had an author field that was the author of that comment. So by ensuring an index on comments.author, what this is doing is this is going and telling the database to go through all the book documents, and for every book document, look at all of the comments, and I want you to create an index on the author field of all the comments. So now that lets me do queries like db.books.find, comments.author, Kyle. What I'm going to get back from this query is all of the books that Kyle has added a comment on. You can also do things like ensure an index on the number of votes, right? So this is now an index on the votes field, and this lets me do a query like, find me all the books that have greater than 50 votes on one of their comments. So this is a really powerful technique, right? It lets me do a lot of data, lets me store a lot of structured information. It's all grouped together sort of by the high-level entities that I'm actually thinking about in my code, and I didn't need to go through a process of normalizing this data. I can store this all in a single document, and typically, like I said, if I'm building a new competitor to Amazon.com and I'm selling books, book is the natural unit that my application is working with, and so it makes sense to have all this information grouped together. Now, if you want your database to go fast, these rich documents are the way to do it. So as I mentioned, there's a couple of things that make this really powerful. First of all this information is stored together on disk. Right, so normally in a relational database, if I had 6 different tables that I needed to join together, all that information is spread out in different areas of memory, different areas of disk. And so in order to fetch that whole book document back in a relational database, I'm asking my computer to do a lot of work. I'm asking it to go to the books collection and get the information about the book. Then I'm asking it to go to the authors table and get information about the author. Then I'm asking it to go to the comments table and get all the comments for the book. All of these are slow operations in a computer. Accessing disk is slow. So the more data locality I can exploit, the faster my queries are going to run, simply because the disk drives in my computer have to do less work. The other thing that happens is that the query planning phase of the database is much, much simpler. So in a relational database, when I have complex joins, my query planner has to figure out, okay, for this query that's matching 10 different attributes and joining 6 different tables, which table should I start looking at first? And oftentimes it'll pick the wrong one. There's a lot of science and a lot of PhDs that have been granted to people for figuring out great ways to optimize SQL queries. But in MongoDB, the query language is much, much simpler. You're always sending a query to a single collection, and so that dramatically simplifies the query planning stage of the database. And so there's a lot less overhead to actually processing a query before you actually start going and loading things off of disk. We like rich documents. They're fun to work with. It's a lot easier to think about your book and all its comments as a single object in many cases than it is to try to completely normalize your data model. And sort of as a counterexample to this, we have things like this. Right, so this is the entity relationship diagram for Magento, which is an open source e-commerce platform. And so Magento is a really powerful e-commerce platform, but it's really complicated. You can see here there's a massive number of tables stored inside of Magento. And so what this means is that, first of all, if I'm trying to extend Magento to do something new, it's often very, very complicated because there's lots of moving parts inside the database. Similarly, if I'm trying to fetch information or update things inside this database, it's going to be very complicated because I need to update lots of different tables, I need to do lots of complex joins, and things are going to tend to slow down. So by contrast, in MongoDB, documents can be very rich. So for example, here is a sample purchase order document. Now, this may or may not be realistic for your application, but what's interesting here is that I can store all the information for my purchase order in a single document. Here I've got an array of line items in my purchase order of the SKUs of the various products that I'm going to buy. I've got the address of where I want to have these items shipped. I've got the payment information with the credit card details and expiration date. I've got the subtotal of how much this whole shopping cart is going to cost. And all of this is stored in a single document. It's much easier to reason about this than a more complex relational model for many types of problem domains. So now, let's look at some of the common data patterns we see and how we actually go about modeling these in MongoDB. So inheritance, right? We take it for granted. We use it all the time in any object-oriented programming language. And you typically are, doing things like this. I've got an abstract shape class, and I say, all shapes have an area, but my system is going to store 3 different kinds of shapes: circles, squares, and rectangles. And each of those different shapes has different parameters that specify it. So a circle, I need to store its radius. A square, I store the length of each edge. And a rectangle, I store its length and width. Right? So in object-oriented language, if I'm modeling this in Java or Ruby, I might use a simple inheritance tree, have a shape class, and then extend that with various subclasses to model the various attributes. But as we all know, when you try to map this to a relational database, it gets complicated. You probably end up with something like this. So single table inheritance is commonly how you solve this in RDBMS. So I have a table in my RDBMS called shapes, and I have what we call a sparse table. So I have all of the attributes for the base class and all of the subclasses modeled inside my single table inheritance model in the RDBMS. And for each row, depending on what actual subclass we have, only a subset of those fields are filled in. Now, this has a few limitations, right? Obviously, first of all, if I want to add a new subclass, I need to go and modify my schema and add a new column for that subclass's attributes. It also means that my table is very sparse. If I have hundreds of subclasses, each individual row is likely to have a very small subset of those columns with actual values. This can make it very difficult to query this data, and in many databases it can be very space inefficient to store this because I actually need to store space on disk even for these columns that I'm not using. All right, so how do we go about modeling this in Mongo? Well, in Mongo, because every document can have its own attributes, there's no need to do this sort of sparse table model inside of Mongo. So when I say db.shapes.find, here you'll see I've got a circle, a square, and a rectangle, and each document, depending on its type, has different attributes. Right? So MongoDB doesn't care what attributes you have inside the documents in a collection. It can query them all just fine. So here I've got 3 shapes in my database, and so let's say I want to go say, find me all the shapes where the radius is greater than 0. So I can say db.shapes.find radius greater than 0. Now, what's interesting here is that many of these documents don't even have a radius field, right? So the way MongoDB handles this is essentially the query planner runs through the documents and it only considers documents that actually have a field called radius, right? So it's going to automatically exclude squares and rectangles because they don't have a radius attribute. Now, I can also index on these fields. So sparse indexes allow me to index on attributes that only a subset of my documents have. So first of all, just defining db.shapes.ensureIndex radius:1, if I exclude the sparse true attribute, what this is going to do is it's going to create an index on the radius attribute. That's pretty obvious. The default behavior of ensureIndex, though, is that if a document does not have a field, it gets inserted into the index as if it had a null value. So if I exclude sparse, that means my index would have all 3 shapes in it, but there would be 1 shape that had a radius of 1, and there would be 2 shapes that had a radius of null. When I use a sparse field, what this does is it tells the database to exclude from the index any documents that don't have a value for that field. So that's going to dramatically compress my index because it means that if only 10% of my documents have a radius attribute, my index only needs to cover 10% of the actual documents in the collection. So this could be a great space saving. It's also going to make things a bit faster because that index is going to be smaller. Another common data pattern that we tend to model is one-to-many relationships. And there's not necessarily a hard and fast rule about exactly how to model these types of relationships. One-to-many relationships might specify a weak association, it might specify a composition or an aggregation, and so depending on the semantics and ownership of these relationships, there's different ways you might want to model it. Right? So one way to model one-to-many relationships is to use an embedded array or array keys. So, for example, if I have a user document and user has a number of blog posts, I can store a blog post attribute that has an array of all of the IDs of the blog post that user has created. Now there's some helpful things that I can do with this. So I can use the slice operator to retrieve a subset of that. So for example, slice lets me say, find me the first 5 blog posts, basically the first 5 elements of the array. However, sometimes it can make queries hard, right? If everything's stored in arrays like this, it's difficult, for example, to find the latest comments across all of the documents that I've commented on. So another way to do this is with an embedded tree, right? So rather than having the array with references to other things, I can store essentially nested documents that store attributes and documents hierarchically, right? Much like we talked about having the comments embedded inside of the document, that can be modeled this way. So again, you want to think about this in terms of, try the data model out with several different patterns and see what the query needs of your application are and how naturally that representation can be queried for your use case. So another way to do it is the sort of more traditional way of normalizing your data. So, for example, going back to our comments example, in the earlier example, we had our blog post, and then comments were stored as an array of documents inside of it. Now, another way to do it is to actually have comments be its own collection, right? And then, this is more like how you would model it in an RDBMS. So each comment might have a reference to the ID of the blog post that it's from, and that's going to be very flexible to query. However, you're going to lose some of the performance benefits of data locality, right? Because now, much like an RDBMS, when you go to fetch a blog post and all of its comments, you need to go to multiple places on disk in order to fetch all that data. So again, there's sort of a decision process you go through, and you've got a lot more tools inside of Mongo for how to model these kinds of things. You can store things embedded inside the document. You can normalize things, although keep in mind you're going to need to do that join within your application. The database is not going to do that for you. So as we look at the different ways of doing this, you want to think about the ownership pattern, right? So if if an author is an aggregation of or a composition of a number of blog entries, then I might look at storing those as an embedded array or using array keys. If I have more weak associations, I might use an embedded tree. So instead of having an array of all of my blog posts, I might have a document where the keys are the blog post names and the values of the blog posts themselves. Or I might go and fully normalize that model and store the things in different collections. So again, this is kind of the array model of storing comments. And this would be a more normalized model. So here we have, at the top, we have our book document, and at the bottom we have a comment as its own document in a separate collection. Here we store a book ID, which is basically a foreign key reference into the books collection. This is going to give me the most freedom with respect to how I query my comments. So it's a lot easier to do things like, find me the last 5 comments that were posted on any blog or any book. But again, this is going to be the least performance of the models because you're asking the database to do a lot more work. The data is spread out more on disk, and keep in mind you're going to need to do joins on your own. So for example, if I want to find all the blog posts or all of the comments on Destination Moon, what I'm going to do is first go query the book document to get the book and get its underscore ID, and then I'm going to use the underscore ID of the book to go find all the comments that reference that book ID. So when you're dealing with these hierarchical documents, you kind of have 2 choices of how to represent them, right? So one is referencing, the other is embedding. So when I reference something, it's much like the foreign key model from the previous slide. I can, within my document, store the object ID or some other key that allows me to perform a second query into another collection to get the thing I'm looking for. Embedding says, I'm just going to put this whole document inside of the outer document. right? When I embed things, I tend to get more performance. When I reference things, it tends to give me a little more flexibility with my queries. It really depends on what you're looking for in your application. And again, the rule of thumb is generally, it's so easy to try out different models in Mongo that, it's very easy to rapid prototype your data model and try it out with different approaches to see how easy it is to query and how well it performs and how efficient your indexes for your data model are. So now let's look at many-to-many relationships. So in this example, let's say I've got products and categories, right? So a product can have many categories, and a category can be in many products. So modeling this is a little trickier. Obviously, you're not going to be able to necessarily embed all of the information in order to make this work. So one of the ways we could do this is we can have a products table, and so in every product in our products table, we can store an embedded array of category IDs. So this allows me to reference this product is in these categories. Now separately, I can have a categories table, and each document represents a category, and every category can have a list of the product IDs that are in that category. So what's notable here is that in a relational database, I would need a third table. That's like my join table that represents these relationships. In Mongo, I can do this with just the two collections that exist. So I got products and categories, and each one contains an array of references to the other. Now, depending on the update rate and the dynamism of this model, this might be a pain. Right, because it means that if I ever add a new category, add a new product, I potentially need to go update multiple documents in order to add that. So depending on how static this type of relationship is, this may or may not be a good way to go. Right, so incidentally, on this model, I can define indexes on the products and categories, and this makes it really easy to go search through it in either direction. So another alternative is to actually only store the relationships on one side. So in this model, we've got our products collection, and it contains a list of categories that product is part of. And then we have a separate collection of categories that has the information about the category. So in this model, I only store the association on one side. But it turns out I can actually still perform most of the queries that you would expect off of this model. Right, so if I want to find all the products in a given category, I can say db.products.find and specify the category IDs that I'm looking for. That'll give me all the products. Now, if I want to say all the categories that a given product is in, I can first go query the product, say db.products.find, and give it some ID, and that gives me the actual product object, which internally contains the list of categories. And then I can say db.categories.find, where the ID is in the set of category IDs from the product. So now I'm leveraging the in query to say, here's a set of category IDs. Go fetch me all these category documents. Right, so now I can do this query in both directions. I can get all the products for a category, and I can get all the categories for a given product. I only needed to store the association once. I also only need a single index here on the category IDs nested attribute in order to make this query fast. So another common problem is modeling trees. This tends to be a tricky thing in any database. One of the nice things about MongoDB is that, because you can store hierarchical documents inside of a single document, it tends to be pretty easy to represent an entire tree inside of a document. So, for example, imagine I've got, not just comments, but threaded comments, so I can respond to an individual comment. Well, I can store that as a big tree, where I've got, the entire document is the whole set of comment threads on a particular book. At the top level, I've got all the top-level comments to the book. Underneath that, I've got all the responses to each comment. So in this document example, I've got an array of comments, and then within the comments, I see an array of replies, right? And so now I can store this whole tree of comments inside a single document. Right, so the pros here, it's a single document. It's going to be very high performance. It's relatively intuitive because it kind of looks as you would expect it to look when you're looking at the comments thread, say on a web page or inside your application. But on the flip side, it's a little hard to search. It's difficult to get partial results. right? So if I want to go find all of the comments from Kyle, I'm going to end up getting the entire comment thread, including all the comments, where Kyle's was just one of them. Also, in MongoDB, you need to be aware of your document limit. So each document has a maximum size of 16 megabytes. So you want to make sure that, if you're going to model data this way, you don't want to run up against the upper limit on your maximum document size. So another way of storing trees is to use parent and child links. So with parent links, each node is stored as a document, and you contain the ID of your parent. With child links, each node contains the ID of its children, and actually with child links you can support more complex topologies like graphs where you have multiple parents for a single child. So let's look at what that looks like. So here we use a model we call the array of ancestors. So each document here is a node in my tree, and my ancestors basically it's an array, and it's the path from myself back up to the root of the tree, right? Parent refers to the node immediately above me in the tree, right? So here I've got A, B, C, D, E, F. I can see the ancestor path for each node in the tree and the immediate parent of each node in the tree. So if I look at like node F, right, its parent is E, and E's parent is A, hence the ancestor path is AE, right? And I can see E in this collection as well. Its ancestors are A, its parent is A. Now this model, again, if you're going to be changing this tree a lot, this can be a little more complex to update because if I want to, say, reorganize the middle of my tree, it's going to be hard to make those updates and maintain this. However, this model, if it's relatively static, I can actually query very efficiently, and I can do a lot of very complex operations on the tree with relatively simple queries. So for example, if I want to find all the descendants of B, I can say db.tree.find ancestors:B. Right, so here we're leveraging that multi-key index where we can say, find me any document that has B anywhere in its ancestors list. So even people that are 10 children down from B will be included in those results. And if I want to find the direct descendants of B, I can say db.tree.find parent:B. And so obviously the parent is just the immediate parent, and that lets me get directly to the direct children of B. If I want to find all the ancestors of F, I can say db.tree.find and go get the document for F. F includes its list of ancestors, and then I can go fetch from that list all the individual documents for its parents. So this is useful for storing things like taxonomies or hierarchical categorization, say in a product catalog. Another common pattern is a queue, right? So you might, for example, be building like a background job processor, and you want to keep track of all of the jobs that your system is processing, and you want to make sure that each job is only run once. So what I might do is store a collection in Mongo where each document represents a job. Now, inside this document, I've got a status field, the in progress, which says whether or not this job is actually running. I can store a priority, which says, what's the priority of this job relative to everything else. And then I've got some, message inside of there that reflects, what this job actually is. So now, for inside my application, I want to go find the highest priority job and mark it as in progress. So this is sort of the query that my worker task would run to, allocate a job for itself and start working. So here I'm going to use a new command that we haven't seen before, the find and modify. So find and modify, what it does is it's an atomic compare and swap operation. So when you say db.jobs.find and modify, I specify a query. So I'm looking for jobs that are in progress. I specify a sort. So I'm sorting by priority because I want the highest priority member that has in progress set to false. And then I specify an update where I want to set in progress to true, and I want to mark a timestamp of when I started. So what this is going to do is this is going to atomically find the highest priority job that is not currently in progress, mark it to in progress, and give it a timestamp. So this ensures that only a single client in the database will get allocated this single job, and I can manage my jobs fairly easily without having to introduce a separate message queue or other type of system to manage those jobs. So that reaches the end of our presentation here, and in a moment I'll start answering some of the questions that have come in while we're going. And I think, obviously modeling data for a document-oriented data store is pretty different than a relational database. A lot of the things you know from a relational database are going to carry over directly, right? So, you can still do foreign key relationships inside a document database. The only issue is that your application is going to need to go fetch those foreign key values. The database doesn't do joins for you. But that doesn't mean you can't use them. Some of the main concepts are that, use this hierarchical nature to your advantage, right? You're going to get huge performance benefits by data locality and storing information together so the database can access it more efficiently. There's a lot of data models that actually are much more natural to model in this kind of document model, things that have a more hierarchical nature where I can store it inside a document, things that have arrays and lists of things that are more complicated to model in a relational database. And because it's all a completely dynamic schema, I have a lot of freedom to extend the schema and have a high degree of variability in the actual fields stored inside the database. So hopefully this was useful. I went through kind of the core concepts of modeling documents and how we queried it, and gave you a few examples of basic data models and how you can actually access those models with Mongo. Now with that, I'm going to jump over to the Q&A tab and see what we've got here. So one question. If you want to constrain what values could be used as tags for books, how could that be done? Well, things like constraints, basically you're going to be, typically you're going to be enforcing those kinds of constraints at your application level. So the database doesn't have any notion of constraints or restrictions on documents. There's no way I can tell a collection that, field X can only have values of, 1 through 5. So if you want to actually enforce those kinds of constraints, typically you're going to need to devise a way at your application level. Now, to some database architects, that'll sound like blasphemy. To other software architects who say, you know what, in my Rails application, Active Record does a great job of enforcing validations on documents, or with Spring Data in my domain model, it's very easy to express these constraints there, and I'd rather have those constraints live in the code. That's sort of our philosophy, that these constraints typically live in your code also. You're not always relying exclusively on the database to do this, and so since you've got the constraint model there, it's typically easier to leave it there. Another question, can you explain something about the scaling of MongoDB? Yeah, so MongoDB scales horizontally with a technique called sharding. So with sharding, basically what happens is given a collection of documents, you choose some field inside that collection as your shard key. So for example, let's say we are sharding our books collection. I might shard it based on the title of the book. Now, what MongoDB is going to do is if I have 5 database instances, it's going to spread all the values of book title evenly across those 5 databases. As I start inserting books, it's going to look at the title field of the book and automatically send that request to the database that holds that range of the data. So what this does is it gives me a great degree of parallelism, right? Because as I can now add more servers to my database, and that spreads my data out over more and more compute and storage capacity. Now MongoDB is totally dynamic, so if I add a new server, it's automatically going to spread the data out to use that new server. I can also take servers out of commission. It'll move those documents off of that server onto the remaining ones. So what this means is that, first of all, MongoDB is very high performance on a single node. But once you exhaust the performance of a single node, you can start adding more servers to your cluster, and the database is going to scale pretty well just by adding more computers. So here's a question. A document has a limit of 16 megabytes. The document corresponds to a row and not the entire table. So a table and still have millions of documents with each document up to 16 megabytes. Yes, you're correct. So each document is limited to 16 megabytes, but a collection can contain, a collection basically has a 64-bit address space. So you can have, however many 16 megabyte documents that you can fit in the 64-bit address space, which is a lot. How do you govern the different fields and make sure you don't have slightly different names of what should be in the same field? Is there a schema analyzer? So that's a great question. I think, again, like with the earlier question about constraints, typically you're enforcing this at your application level. Now, you can run into situations where you push a version of code, and I used to call it username, and then somebody changed the code to call it user. And so, you might be forced to deal with situations like that. Typically, we ask that you, try to enforce these things at your application code. And, the way most people implement those domain models, it's relatively easy to enforce that. Now, if you do get into that situation, there is a rename command that allows you to rename a field. So you can go find all the things where it said username and rename that field to user. Next question. MongoDB supports multi-column indexes. Yes, absolutely. You can do compound indexes on multiple keys. Each individual key in a compound index can have a different sort order. You can do geospatial indexes. So notably, Foursquare runs on MongoDB, and all their check-ins are indexed via MongoDB's geospatial index capability. You've got sparse indexes, covered indexes, pretty much like most of the features you'd expect from a relational database on the indexing side you can do in MongoDB. So next question, is there a benefit of using dbref instead of just specifying object IDs? So a dbref is basically a convention for storing a reference into another collection. And dbref basically contains a collection name and an object ID. And there's really nothing in the database that's optimized to deal with those. It's really just a convention that's useful in many of the drivers for resolving references and knowing which collection to go to. So I'd say it really, there's not a huge benefit. Some of the drivers interpret them nicely, but storing a list of object IDs works just fine. Next question, how does one refactor Mongo schemas? Say that I've started out embedding documents and articles, but a million articles down the road, I find out that I need more flexibility. So that's a tricky question. I think that basically you're going to need to migrate the existing data into your new model. Now, one of the ways that we found that this works most effectively is to essentially do an incremental migration of the data. So I'll give you sort of a case study of how somebody else did this that worked really well. So Shutterfly had about 20 terabytes of data in their content management system. It was metadata about photos. Now, they needed to migrate that data from their Oracle database into Mongo. So that effectively is a schema transition, and then once they have changed it to Mongo, they went through several evolutions of their schema. Now, what they did is they implemented an incremental transition strategy. So the idea was when they did the initial transition from Oracle to Mongo, they actually added code in their model layer that treated Mongo as basically a read-through cache. So what would happen was when a query came for an object, I would first go to Mongo and try to get the object. If it's not there, I'd go to Oracle, get the object, then store it in Mongo, then return it. So what that does is as my application's running, it's incrementally converting the data from the Oracle schema to the Mongo schema. The same model can work for data entirely within Mongo. So I can fetch a document. I can have code in my model layer that checks whether this document is in the old format or the new format. And at that time, at that point of access, I can transition it to the new schema. Right, so this is a really good way if I've got many, many terabytes of data. It's often going to be infeasible in any kind of data management system to sort of batch convert all that data without having any downtime. So using that kind of incremental approach is, we find, the best way to go. Next question, how would MongoDB perform if your book had 1 million comments? That's a great question, and that's one of the cases where you're trying to decide between using a model of embedding the comments inside the book versus having the comments in external collection. right? So if you expect to have a ton of data, you obviously want to be aware of the 16 megabyte limit and store your data in a way that you're not going to run up against that. So if you expect to have lots and lots of comments, you're probably going to want to have some strategy for separating those comments out into separate documents. Now, it's not just a binary decision. You don't just either store all the comments in the book or store each comment individually in a document. There's actually a great presentation from our CTO Elliot about a hybrid approach where I store comment collection documents, each of which stores, say, 100 comments. And so this is sort of a hybrid approach. So I'd have my book collection, then I'd have this collection of clumps of comments. And so instead of going and get one document for each comment, I get batches of comments, 100 at a time. If you go to tengen.com/presentations and look for the Schema Design at Scale presentation, you'll see that model described in detail. Question, does updating a single document lock entire collection or DB? So MongoDB's locking strategy, it relies on a read-write lock on the MongoDB process. And so when you perform an update, it actually locks the entire process. Now, that kind of sounds scary. However, in practice, it tends to work pretty well most of the time. Basically, what happens is the actual update operation tends to be very, very fast because that update operation is happening in memory. The case where that update operation is going to be slow and where that lock is going to bite you is the case where the object you're trying to touch is not actually in memory and we need to go to disk. So older versions of Mongo had an issue where if I try to update a document that's not currently in memory, it would take that write lock, go to disk, load the document into memory, and then perform the update. Now, that disk access is obviously much, much slower than a memory access, so that would hold that lock for a long period of time. Since then, the last couple of versions of Mongo, we've introduced a number of features like yielding and the ability to predict page faults that basically eliminate that lock in most of the cases where it would bite you. Next question, how do you find documents that don't have a radius field? So there is an exists query operator and a not query operator. So you can do db.shapes.find where not exists radius, and then you would find all the documents that do not have a radius field. So I notice we're coming up on the end of the hour. There's still a couple questions left. I will do my best to collect answers to these questions and try to email them out to the people who asked them. But at this point, I'd like to thank you all for attending. This has been a great webinar with some really great questions. Hopefully it was useful to you guys. And I would encourage you to come check out mongodb.org, where you can get the latest version of the software and access all the documentation. And also check out tengen.com. Tengen provides commercial services around MongoDB. There's a ton of presentations and talks up at tengen.com/presentations. And please do attend our next Mongo conference when it's coming to your area. Check out tengen.com/events for more information. Thank you very much.